Okay, so welcome to part 5 of the video on expectation values. So what we've done so far is we've imagined splitting up our sample space into the sets which are all mapped onto a single x value. So all of the points in each of these little subsets of the overall sample space are mapped onto a single x value. Okay, so the reason that's a good idea to do is that now the y value you would have to get in order to be successfully mapped onto for x plus y to successfully map you onto a is fixed. For a subset of each of these, so if we divide it up like this, a subset of each of these sets is going to be mapped correctly onto, so all of these bits here are going to be mapped onto by x plus y are going to be mapped onto a. And now if you are in this set and you're mapped onto a, then your y value is set. So for instance, if your x value is x, because all of these points in here, their x value is x1, so if you're in this little bit of this set, this is a subset of the overall set, which is the bit that's going to be mapped onto a by the random variable x plus y, then your y value must be equal to, x plus y must be equal to a, so y must be equal to a minus x1. Okay, so basically you can do this for all of them. Your y value here must be a minus x2, a minus x3, etc. What happens is that this is in fact, because x1 is a random variable, so because x is a random variable, the inverse image of each point, so x inverse of x1, which is this set here, this is the inverse image of x1, all the points in the probability space which are mapped onto x1. And in fact, we could put this as an I, so for all these xi, all of these sets that I've partitioned the sample space up with, they are all elements of the set of events, so they are all events. In addition, because y is a random variable, or y inverse of a minus x1, so the set of all points which are mapped onto a minus x1 by the random variable y is also an element of f. So their intersection, x inverse of x1 intersect y inverse of a minus x1, is also an element of f by the axioms that this set of events obeyed, that it was a sigma algebra. So remember, the axioms of a sigma algebra are that it has the empty set, the whole space, it's closed under complement, so if E is an element, E complement is also an element, and it's closed under countable unions. But because of the complement rule, along with the rule that it's closed under countable unions, you also get that it's closed under countable intersections. So that's how we know that this intersection is an element of the set of events as well. Which means that this set down here, this set that I've shaded dark black there, which is the intersection of y inverse a minus x1 with x inverse x1. So of course this set is not equal to y inverse a minus x1. There could be, y could take that value and x could take a value different from this. This is the set that x is equal to x1 and y is equal to a minus x1, so it's the intersection of those two sets. So this is an element of f. Now, if we union up all of these little sets here, that is equal to the inverse image of x plus y of a. So the union of all of these sets here, this set here, is x plus y inverse of a. Now, this set here is x inverse of x2 intersection y inverse of a minus x2, and all of these you can go so on. They are all elements of the sigma algebra of events. So when we union them all together, that is also an element of the sigma algebra of events, which implies that x plus y inverse of a is also an element of f. So that is how we know that this new random variable is indeed actually a random variable.